So these have been examples of questions where the rod or the beam or whatever it is in equilibrium. It's definitely not moving. What we're now going to look at next are questions where the beam instead is on the verge of tilting. So it's still technically in equilibrium, it's still technically not moving, but any slight change would cause it to lift up on one end or the other. So let's just see what such a question is going to look like. For now, just have a glance over these. We have, for instance, in this first example, a uniform rod AB has length 3 meters and a mass of 4 kilograms. Find the magnitude of the reactions at C and D. Well, this first example actually isn't mentioned in tilting. The tilting is going to come a little bit later. First of all, this is actually just in your usual state of equilibrium. So actually, again, let's just see. Could you pause the video and see if you could work out what those individual reactions are going to be? They're not necessarily going to be the same. So as before, first of all, we're probably just going to want to label on what forces we have. Because this rod has a mass of 4 grams, and we're saying it's uniform, we're going to have a weight coming down right in the middle of 4g, 4 times gravity, and that's because the whole rod has a length of 3 meters and it's a uniform, so this will be halfway. This will be 1.5 meters here. We then have our individual reaction forces, and again, because we don't know that they're the same, we can't assume they are, so we'll have to label them individually. With this in mind, we could, if we wanted, get an expression in terms of the vertical. We could say that downwards of 4g has to equal RC add RD. Actually, I might as well make a note of that for now, just so we have it. It's going to be it'll be up to you whether you want to use that later or not. There's a couple of ways you could go about it. Either way, though, what we should probably at this point do is try to get some moments. So if we, let's say, want to get the reaction at C first, we'll want to eliminate the reaction at D as an unknown. So let's take D as our pivot. So we pivot at D. For your clockwise moments, so that's what would make either B go down to this way or A up this way. That's going to be your RC. So RC is that force, and we can say that if A to D is 2 meters and A to D is 0.5, then C to D must be 1.5. This, as the one clockwise moment, would have to be the same as the one anti-clockwise moment, because we're saying it's an equilibrium, which will be your 4g times by, and to get the distance to the centre of mass to D, we'll say, well, A to D is 2 meters, and A to the centre of mass is 1.5, leaving a difference of 0.5. So just expanding the brackets, you would get that 1.5 times the reaction at C equals 2g. Therefore, just divide the 1.5 over, you're left with the reaction at C equaling 4/3 g. Now, to then get the reaction at D, you could indeed now just do, so if you now replace that RC here with 4/3 g, 4g minus the 4/3 g, and that would leave you with RD there. Or if you wanted, we could take moments again, and again just talk through that in case that's the method that you did. So we would have our pivot at C now. So now we're going to be going from here. For the clockwise, this will now be your 4g. That's because we're now on the other side of the pivot this time. This same 4g would now be trying to go in a clockwise manner. So 4g times by, and if the A to centre of mass is 1.5 and A to C is 0.5, that leaves this as a difference of 1. And that's going to equal this missing RD here, because remember now RC is eliminated because it's on the pivot itself. So the RD times by that same distance we worked out before of 1.5. So 4g equals 1.5d, therefore divide by the 1.5, your RD is going to equal 8/3g. Again, what you would have got if you had used that vertical equilibrium expression instead. Okay. Well, now that we have these, we're then told about some other things. We're told a block is placed at B. So, okay, we're now going to add some other thing here. We don't know what the mass of the weighted thing is going to be, but we know it's going to have a weight, so we can just put an arrow coming down here of W. Now the rod is on the point of tilting at D. I'm just going to find the weight. So okay, this is where we're now getting into that idea of tilting that I just mentioned before. The idea that if this had been the tiniest bit heavier, the plank would now, or the rod would now be lifting up around D as its pivot. So A would be rising and B would be dropping. It wouldn't be tilting the other way because it's not going to be pushing down through the pivot C here. So it's lifting up from C. Now the difference this makes is if we're on the point of tilting that any further you wouldn't be touching C anymore, this gets rid of the reaction at C. It might as well not be touching anymore. But now again, yes, we have this instead, this new, if we're focusing on D as a pivot, clockwise moment of W here. So how are we going to work out what the weight is here? This time we can't go straight into working out our vertical equilibrium because we don't know what this RD is either. All we know is like 4G plus W equals RD. Not massively helpful. But if we were to go straight into looking at moments, because we'd be taking D as our pivot this time, definitely because it's tilting around D, that would eliminate the RD here. Therefore, we can just work through our moments as we usually would without worry of that second unknown. So if we say that we pivot at D, the clockwise moment, as I say, will be this W, because it's going to make the rod spin this way around. So W times by, if the whole thing is 3 meters and AD is 2 meters, that just leaves D to B being 1 meter. This will equal, for now, because remember, even though it's tilting, it is still just in equilibrium. So it is still going to equal this anti-clockwise here of your 4G times by, and again, that distance of the center of mass to D is going to be 0.5 again. Therefore, you can say that W is going to be the same as 2G newtons coming down there. Well, now that we have that weight, we can say, well, find the magnitude of the reaction. Now we can look in vertical equilibrium. So we can say that the downward forces of your 4G plus your 2G, which again we now know is the weight, that's going to equal the upward force of the reaction at D. Therefore, the reaction at D will just equal a sum of 6G newtons. So just to reiterate, that is how we're going to use the idea of tilting to change the scenario slightly. So if you're tilting at a specific point, then you're going to take that point as your pivot, most likely. Then more importantly, we're saying that any reaction force or any tension at what would have been the other support disappears. So if we now turned back to one of the types of questions where you have a rod being suspended by ropes, so we'll have a rod A, B here, suspended by these ropes. This isn't going to have tilting again, but it is going to have something else that's different, and that should become pretty clear as soon as we start reading this through. Non-uniform rod AB with mass 15 kilograms has a 10 kilogram mass placed at C. Now, it is held in equilibrium by two light inextensible strings. Given that the tension in the string at A is 10 newtons greater than the tension at B, find the distance between A and the center of mass. So, non-uniform rod. Mentioned this before, saying obviously the opposite of a uniform rod. There will be a center of mass, a point where we can imagine all of the mass acting, but it's not in the middle. It's at some other unknown location. So if we were to try to just make annotations of this, say, well, definitely we know that the mass here at C has a mass of 10. So coming downwards, that would be a weight of 10G. Obviously, you're going to have tensions in the strings coming up here. Now, the tension in the string at A is 10 newtons greater than at B. So it's not saying it's 10 or 10 times, it's just plus 10 essentially. So if this was T here, this would be T plus 10. Now, we still do have to obviously annotate the weight of the rod itself, which is we don't know what it's going to be. So really you can put this any way you want. So let's just say, I'm going to stick it in the middle anyway, even though again we know it's not in the center. We'll just say that's 15 G here, and that this distance here, and specifically going to A rather than B, even though this obviously overlaps with the other annotation, is that is the distance we're specifically trying to find in the end, the distance between A and the center of mass. So let's call that X meters, or centimeters rather, to be in keeping with the other units up here, because we have the distance between the strings is 200 centimeters, and that the distance between A and C is 40 centimeters. So to start off with, because we have multiple unknowns, none of which are going to be completely got rid of by one particular method, we're going to want different equations that we're then probably going to make the same as each other. So if we were to first of all want to look to make an equation for vertical equilibrium, I'd like to think, what would that look like? And then, how could you actually potentially use that already to find out what one of the unknowns is? So again, just pause the video briefly and just try to work that out for yourself. Okay, so because when we're doing vertical equilibrium, we're looking at the downward force equaling the upward force. So the combination of the downward forces would be your 10G plus your 15G, and the upward forces are going to be that T plus 10 add the other T. So just simplifying this, you end up with 25G equals 2T plus 10. Therefore, T is going to equal 25G minus 10, of which you could either do as 25 over 2G minus 5, or 12.5G minus 5, or if you prefer as a single decimal value, if you put that in the calculator, you would get that to be 117.5 newtons. Well, now that we know this tension, now that we've stopped this from being an unknown, we're just left with one other unknown, that distance. And because that's a distance, we can now return to our principles of moments. Because we're looking at the distance between A and the centre of mass, we're probably going to take A as our pivot. So again, just acknowledge, you're going to pivot at A. From this, for the clockwise moments, that's going to be your two weights. So you're going to have your 10G times by that 40 for 40 centimeters, added to the 15G, and that's times, the best we can say is the X centimeters there. And that is going to be equal to the anti-clockwise moment of T here, again, because we're taking A as our pivot. We don't have to think about the T plus 10 because that would be a zero moment. So here with T, or the 117.5, as we know it to have a value of, times by that distance from A, perpendicular distance, of 200 centimeters. Just expanding these brackets then, you'd end up with 400G plus 15GX equals to 23,500. So to get X on its own, we would take that 23,500 minus the 400G from it, and then divide that by 15G here. You can't cancel through by a common factor of G this time because there's no G in that first term, so you're just going to have to type that all into your calculator using your 9.8 instead of those G's, and then this would come to approximately 133 centimeters away from A. That is the center of mass.